Today we're going to introduce two new reaction patterns. We've already looked at synthesis and decomposition. Now we're going to look at single replacement, and then very briefly we're going to look at combustion. And along the way we're going to talk about an important class of reactions called redox reactions that could be synthesis or combustion or single replacements that we'll see quite often. And this has something to do with the oxidation numbers that we learned how to assign earlier on in the year. First we're going to start out with a little review of the 5 reaction types. First of all, we had synthesis reactions. These are the synthesis or creation of one product from multiple reactants. We also saw decomposition reactions, which are about the opposite. You start out with one reactant that has to be a compound, and it decomposes into 2 simpler substances, which are often elements. Single replacement reactions, which we'll look at today in more detail. You start out with an element and the compound. Those are the reactants. The products are a different element and a different compound. And there's a replacement of one substance for another there. Double replacement reactions, which we won't look at today, are compound, like AX, and another compound, like BY. And there are 2 replacements that take place. So you end up with 2 compounds, AY and BX. We'll look at those next time. And then combustion reactions are something combining with oxygen. So something could be a number of things. We'll look at this in more detail today. With O2, and it's going to produce an oxide, like AO something. And this could be a compound as well. In single replacement reactions, we have an element that reacts with a compound, and it's going to produce an element and another compound, a different compound. So there's this consistent pattern in single replacement reactions that allows us to spot single replacements right away. So again, the generic equation, element plus compound makes different element plus a compound. Predicting the products of a single replacement reaction, well, there are several different possibilities, and it takes a little bit of practice, and you have to know some patterns, but it can be done. So we're going to look at several different possibilities and then start to look at how all kinds of reactions fit into these patterns. First pattern is if the element in the reaction is a metal, it will replace the metal that's in the compound. I have a metal by itself, that's my lone element, and here's a compound. That compound has a metal in it. So this metal, the aluminum, will replace this metal. Now here's what replace means. Aluminum is going to go where iron is, part of a compound. Iron is going to go where aluminum is, not part of a compound. So the iron is just by itself after the reaction. And it's not diatomic, so I just write Fe. Never mind that it says 2 there. If it's not diatomic, it doesn't get a subscript. Now, aluminum is going to be part of a compound. Well, aluminum is a column 3, so that makes it 3 plus. Oxygen is a column 2, so that makes it 2 minus. So after I do my charge swap, there's my formula, Al2O3. This reaction isn't balanced. If I wanted to balance it, I'd have to do a little more work. Oxygen's okay, but iron isn't. I need a 2 in front of iron, and I need a 2 in front of aluminum to balance. You try this one. Well, here's your answer. Silver is the lone element here. It's a metal. It's going to replace another metal in the compound. So the silver and the gold are going to replace one another. That means gold will be by itself, because that's what silver was doing on the left-hand side. And the silver is now going to be part of a compound with nitrate. Silver is 1 plus, nitrate's 1 minus, so charge swap gives me AgNO3. Now, this isn't balanced. I'd need a 3 there if I was going to do that, in front of the silver to balance the nitrates. And that means I need a 3 here to balance my silver. Here we're going to see an example of a single replacement reaction. This reaction is going to have a piece of copper wire, and it's going to be reacting with some silver nitrate. Copper and silver are going to replace each other, so that means I'm going to get copper nitrate. This will turn out to be copper 2 nitrate. And copper ions show up as blue. You'll see that happening in this reaction. And silver is going to be by itself. Well, you're going to see that as fuzzy silvery stuff on this piece of copper wire. Notice the blue color, that's the copper ions in solution, and all that fuzzy silvery stuff that appeared, well, that's really silver collecting on the copper wire. Here's another rule for single replacements. If the element in the reaction is a nonmetal, it will replace a nonmetal that's in the compound. Here's an example. If I have sodium iodide reacting with chlorine, this is a nonmetal. Chlorine's a nonmetal. It's the element that's by itself. Well, when a nonmetal is by itself, it's going to replace a nonmetal often that's part of the compound, and that would be iodide. So the chlorine and the iodide are going to switch positions. That means iodine is going to be by itself, and iodine's diatomic, so it's I2. The chlorine is now going to become part of a compound with sodium. Sodium is 1 plus, chlorine's 1 minus, so NaCl is the compound. This isn't balanced, but a 2 here and a 2 here balances. You try this one. Well, here's your answer. Fluorine's the lone element, and it's a nonmetal. Nonmetals replace other nonmetals. So the fluorine is going to replace the chlorine. That means chlorine's going to be by itself, because that's what fluorine was doing before the change, so Cl2. Don't worry that chlorine is 3 on the left-hand side. It's going to be 2 over here because it's diatomic. Then fluorine's going to become part of a compound with aluminum. Aluminum is 3 plus, fluorine is 1 minus, so AlF3. This isn't balanced. I've got 2 fluorines on this side and 3 on this side, so a 2 here and a 3 here will balance with 6 fluorines. That means I need 2 aluminums, so I'll put a 2 here. 2 aluminums in front of AlCl3 means I need 6 chlorines, so a 3 here finishes it off. Here's a single replacement reaction where a nonmetal replaces a nonmetal. In this flask here, the guy's got some bromine. It's dissolved in water. That's the orange-colored stuff. In this test tube here, he's got some potassium iodide. In this test tube here, he's just got ordinary water, and that's just for a color comparison. And in this side, he's got a solution of potassium chloride. Now watch what happens as he adds the bromine to all 3 test tubes. You can see what's happening here. In the test tube that had the Ki in it, the replacement reaction took place and iodine was formed, I2. That's that dark colored purple stuff. That's iodine. In this test tube where there was only water, well, the bromine was just diluted a little bit, so it didn't look quite as orange as it did before. And the same thing is true here. KCl is a product in the potassium chloride test tube. It just diluted a little bit. Nothing really happened. We have 3 important exceptions to this rule that nonmetals replace nonmetals in compounds. One of them is this. Hydrogen will often replace metals when the metal is part of a metal oxide, and it'll give that metal pure and then water. Here's what I mean by a metal oxide. An example is this compound here, Cu2O. It's a metal, copper, that's combined with oxygen. That's a metal oxide. When metal oxide reacts with hydrogen, the hydrogen can replace the metal. So in this case, H is going to replace Cu. Well, the H replacing Cu is always going to give water. The hydrogen replaces the metal in the metal oxide to always give water. That means the copper is by itself. Copper is not diatomic, so it's just Cu. This is not balanced. If I were going to balance it, the hydrogen and the oxygen are okay. All I'd need to do is put a 2 here for the Cu. Try this one. Okay, here's your answer. Iron 3 oxide is a metal oxide. Hydrogen can replace metals in metal oxides. So that means the iron is going to be by itself, just Fe. It's not diatomic. The hydrogen is going to make water when it replaces the metal. This isn't balanced. I'd need a 3 here to balance my O's. That gives me 6 H's, so I need a 3 here to balance that. And I need to balance iron with a 2. Another one of these exceptions, carbon will do the same thing. Carbon will replace lots of metals from metal oxides to give that metal, and instead of water, now you're going to get carbon dioxide. So in this example, here's a metal oxide, lead oxide, a 2 oxide. Carbon is going to replace the lead. So the lead will just be by itself. Simply Pb, it's not diatomic. Carbon going with oxygen is going to make CO2. There's our compounds. It's not balanced. I'd need a 2 here to balance my oxygen, which would mean I need a 2 here to balance my lead. Try this one. Here's your answer. This is a metal oxide, so carbon's going to replace the iron. That means iron's going to be by itself, Fe, and you're going to get CO2. Balancing, you got 3 O's on the left-hand side, 2 O's on the right-hand side. A 3 in front of CO2 and a 2 in front of Fe2O3 will balance my oxygens with 6. That means I need a 4 here for my iron, and the 3 in front of CO2 gave me 3 carbons, so I'll put a 3 there. This reaction here turns out to be an extremely important reaction in the production of iron. Iron ore comes out of the ground with Fe2O3 in it, and it's mixed together with some carbon. It's called coke. It's kind of a form of charcoal almost, heated up to really high temperatures, and that's how pure iron is derived. Let's watch the reaction on small scale. Another exception is that some metals will replace hydrogen from acids to give hydrogen gas and then a metal compound. So here's what an acid is. An acid starts with H. It's a molecule that starts with H. We'll define acids in more detail later on, but for now that'll work. A molecule that starts in H, we'll recognize that as an acid for now. So here's a metal by itself. Here's an acid. The hydrogen can be replaced by the metal if the hydrogen's in an acid. So it's going to give a metal compound. Well, this is going to be magnesium with chlorine. Magnesium's 2+, chlorine's 1-, so MgCl2. That's going to leave hydrogen by itself, and hydrogen's diatomic, so H2. To balance this, we'd just have to put a 2 there. You try this one. Well, your HNO3 is an acid. It's a molecule that starts with H, so H is going to replace zinc. They're going to replace each other. Zinc's by itself, so hydrogen's going to be by itself, and it's diatomic, H2. Zinc is now going to form a compound with nitrate, because that's what's left over when you take the H away, is NO3, which is 1-. So zinc, which is 2+, will make ZnNO3 2, zinc nitrate. This isn't balanced, but a 2 here will do it.